Hello, I'm Sang Kim.
My name is Jisang Park.
And I'm Aaron Walsh. We're going to tell you about our latest results, understanding the chemistry and physics of defects in Kesterite thin-film solar cells. The performance of Kesterite solar cells is much lower than expected, and this can be linked to a low open circuit voltage in operating solar cells. The origin of this low voltage is fast electron-hole recombination.
According to a conventional trap-assisted recombination model, if a defect introduces a deep trap level in the gap, then the defect acts as an efficient recombination center, which is termed as a killer defect. But on the other hand, if a defect introduces shallow levels like donor levels or shallow acceptor level, then it could trap electron and hole efficiently, but it can also donate the charge carriers to the host very efficiently, so it wouldn't act as a recombination center.
So a key question in our study was identifying which defects could be responsible for deep levels and efficient electron-hole recombination. So our starting point was the sulfur vacancy, which in its neutral state results in 2 excess electrons. The surprise that we found is that these electrons become localized on a neighboring tin atom, which in chemical terms can be described as a 2-electron reduction from tin 4+ present in bulk CZTS to tin 2+ neighboring the sulfur vacancy. This, in a sense, deactivates the defect, so no subband gap levels are found, and we would have expected from conventional models quite inefficient electron-hole recombination.
We propose a new recombination mechanism mediated by excited states that occurs in 3 steps.
Step 1.
1+ sulfur vacancy is formed by thermal excitation.
Step 2.
Hole is captured by absorption of IR photons. Step 3. Electrons from conduction band is captured by unoccupied levels near the conduction band of 2+ sulfur vacancy. Overall, this process can limit the performance of Kesterite-based solar cells.
For a full discussion of other defects, please read our publication.
In conclusion, the sulfur vacancy in CZTS is electrically benign without any donor levels in the band gap.
The sulfur vacancy acts as an efficient non-radiative recombination site.
While tin is found as tin 4+ in stoichiometric CZTS, we've shown that tin 2+ and even the metastable tin 3+ state could be quite important in the photophysics of Kesterite semiconductors. So finally, we want to acknowledge our sponsors, the European Kesterite Network StarCell, and calculations were performed on Archer, the national UK supercomputer, as well as Thomas, the supercomputer of the Materials Modelling Hub in London. Thank you very much for your attention.
Thank you.
Thank you.